Let's take a look at the relationship between electric field and electric potential. Recognize one's a vector, one's a scalar, so there's going to be a certain amount of fast and loose, so I'm going to play with a little bit of this. I'm going to try to minimize that as much as possible. So first off, if I have an electric field going to the right, and I put a proton into it, I know the proton is going to move that way. Protons move in the positive charges move in the direction of the electric field. Electric potential, on the other hand, if we think about which way the proton moves, protons move in the direction of the lower electric potential. So this would be V low and V high. So if I am moving from a high potential to a low potential, my change in potential is negative. My electric field points from a high potential to a low potential, so my change in potential is negative in the direction of the electric field. So that's one relationship there. If we look at the basics of it, I have the electric field is equal to kq over r squared, r hat. My electric potential is kq over r times r. Kq over r. So notice that the difference between the two is that this factor of r. So just on a very simple level, my electric field times r would be equal to this, except how do we deal with the vector here? Well, if I want to get rid of a vector and I'm doing multiplication, let's do a dot product, because that gets rid of the vector, creates a scalar product. So as long as r is in the same direction as r hat, which it would be, r vector is equal to the magnitude of r in the r hat direction. So if I do something like that, I now have, this becomes kq over r squared r hat, dot product with r hat. They're in the same direction, so this just becomes kq over r squared times r, which is kq over r, which is my potential. Now, it is not, this is a very fast and dirty way of looking at it, just trying to set up the relationship. In reality, this would be equal to the change in potential. But we've already established that the sign is that the potential is negative in the direction of the electric field. So if I'm going in the direction of the electric field, this actually would have a negative show up. If the electric field is constant in space, then we have the electric field times the change in position is equal to the negative change in electric potential, or the electric field equals the negative change in potential over the change in distance in the direction of the electric field. Now notice the vector symbol is sort of, the vector piece is sort of dropped off. This has built in the assumption that this is in the same direction as that. And so this is something that I will write several times mathematically. It is sort of sketchy notation, but hopefully you'll go with the spirit of what we're talking about. The important thing here is that as long as we're dealing in the same direction, so actually, why don't I put in the r hat there? So the where r hat's the direction of the electric field. So if we wanted to be slightly more formal about it, negative v over delta, whatever direction we're dealing with here. So if I go with a traditional, x, y, and z axes, and that would correspond to an I hat, j hat, k hat directions, then x, I hat, or y, j hat, or z, k hat, or r, r hat. So I have my electric field is equal to negative delta v over delta r. R hat also works just so long as the sort of correspond. So if I have a potential versus distance graph here, that is just the slope of the graph. So I could find my electric field just by looking at the slope of my potential. So if my potential looks like this, my slope is negative the entire time. So that negative times the negative slope makes my electric field positive. And so my electric field would be the slope of that. So it starts out very positive because it's the negative of the negative slope here. And it goes to 0. So technically this is a 1 over r squared relationship, and it's proportional to 1 over r squared, and that's proportional to 1 over r.